Hey everybody, we're back. Thanks very much for hanging. So thanks to Sashi for his presentation, Sashi with Petrobytes. Now for a different perspective, I would like to introduce in Bill Heins, and we'll take about a 10-minute presentation from Bill, and we'll have one more presentation following after. So Bill from Getech, welcome.
So thanks, Jamie. Nice to be here at Pivot 2022. And I hope we do have all hands on deck. Today I'm going to be talking about regional fault mapping from gravity and magnetics for induced seismicity. And that's clearly a hot topic. These headlines from the latest news that focus people's attention on at least the perception that earthquakes and geothermal go together is like deja vu all over again. I came from the oil and gas industry, and we had this question about induced seismicity as well. And we can see that the issues occur in the same geography and because of the same geology. And we can use a lot of the tools that we already know and are familiar with to address the issue regardless of which of the energy systems we're dealing with. And obviously, the first thing you got to do if you want to understand seismicity is to find the faults. And I hope when we walk away after about 8 or 9 minutes, that you will appreciate that mapping those regional basement involved faults is hard work. I mean, you really have to expend a lot of effort. And the hard part is to make sure that you not only account for your own little postage stamp of your lease or your acreage position or your 3D survey, but that the fault network hangs together across a big territory. And gravity and magnetic data is one of the ways that you can do that you can do consistent, confident fault mapping over a big area in the time that's required to get it done. And I'll show you an example just to demonstrate that it really can be done. So let's take a look. I'm going to step you through in the talk 2 different parts of the world, a tale of 2 cities, as it were. On the left, we have the Delaware Basin, or the bigger Permian Basin that I think many people in the conference will be familiar with from their oil and gas lives, and compare that to another place somewhere else on the earth that I'm not allowed to tell you exactly where it is. But there is a big contrast in how brightly the light shines on each of these 2 areas. So in the Delaware Basin, there are a lot of wells. Just in the last decade, almost 20,000 wells, and most of them are horizontal and most of them are really long. So each and every one of those wells investigates a huge volume of the earth. In the other part of the world that we'll be talking about, we have less than 1,000 wells basically since the beginning of time. And most of them are vertical wells, and they are relatively shallow wells, and they only investigate a relatively small volume of the earth. Then there's our other familiar kind of data, which is seismic. In the Delaware Basin, you've got millions of kilometers of 2D and probably tens of thousands of square kilometers of 3D that blanket the landscape ubiquitously. Whereas in the other part of the world, we've got 13,000 kilometers of 2D and only a little bit more than 1,000 of 3D. And all of that is focused in one tiny part of the whole territory. And I'll just emphasize here too, that these maps are at exactly the same scale. They cover exactly the same amount of territory. Just the one on the left has the Latin long because you know where it is, and you can see the counties of Texas and New Mexico in the background. The right-hand side, I'll let you speculate about where that is as we go through the talk. But whether you've got a lot of data or a little bit of data, you still have to find the faults if you want to understand the seismicity. And if we go to the Delaware Basin, we see that the Bureau of Economic Geology has been working on this for quite a few years. And they've really thrown every kind of thing at it that you can. And they've been doing it for years. The publications we'll see just cover the last couple of years, but this is the right way to do it. This is all boots on the ground. This is all the firepower directed at it. This is the full meal deal. And you get an answer that looks like the fault network on the left. And so the preliminary investigation of the big regional fault network was in 2019. Then we have a Bureau publication in 2020 that specifically laid out these faults. And then there's a series of publications in the scientific literature to explain what it means to have all of these faults mapped. And as I said, this is the right way to do it, but this is major mobilization. So what are you going to do over in this part of the world where you don't have that kind of data set? Well, what I'd like to convince you is that gravity and magnetic data are a way to get going on this kind of territory faster and with less effort than we saw in the Delaware Basin. So the first thing you do, obviously, is you get the published geologic maps and you pull off all the faults that people already know about. But mostly those are expressed in outcrop, and they're not really in the places that you most are interested in, down in the Graben, where you saw all the industry activity had been. So we can pull in a little bit of gravity data, we can pull in some magnetic data, and we can start to analyze them in some specialized ways. Very specifically, we can look at total horizontal derivative on the gravity, and we can look at the tilt angle on the magnetics. And we got to put some Greek letters in there just to convince you that this is serious business. But essentially, we're looking for changes in intensity. We're looking at derivatives so that we can look at either a peak or a zero crossing that is likely to have physical meaning in terms of a discontinuity in the subsurface that we're interested in. And got a touchy trigger finger here. The way we do that, in order to do this quickly and objectively, is we have an automated system for doing this that picks out the zero crossings or the peaks and checks to make sure that the phenomenon is observable in both of the data sources. And if it is, then we put a point on the map and say that's likely to be part of a lineament. And so we can then join up all the dots and get to a map. So we start out with an interpretation of the basement lithology. That's a good thing to know in any case. Here, even though we had a bigger geophysical survey, we've just pulled out the information in the specific AOI. And then on top of it, we can map all of the faults that we can see in the various kinds of data. And once we have mapped them, we can use our geological intuition and other geologic information to figure out which ones of them are active and which ones are not. And some of them we won't be able to tell. And we can also categorize them according to the tectonic regime that was likely to have caused them. That the basement mapping helps a lot with that. So in the same way that you saw a colored portfolio of faults that indicated different orientations, we can do the same kind of analysis here with our geophysically interpreted faults as well. Because really, whether the fault moves today or not, whether it's a candidate for induced seismicity or not, depends a lot on the orientation of the fault with respect to today's stress field. So just in the way that the folks in Texas could discriminate among the faults that they mapped by different families, we can do just the same with this kind of interpretation as well. And if you want to read up more about exactly how to do that, there's an abundant published literature, mostly coming from people in our company, that I'd be happy to share with you if you're not able to write this all down very quickly before I go to the next slide. But let's now take a look at the answer you get in a data poor area compared to the answer that you get in the data rich area. And I hope that you would agree that the spatial density and the kinematic interpretation and the robustness, the regional coverage of the interpretation is quite similar between the two methods. Without doubt, the one on the left that has taken thousands of people hours and millions of dollars, or however much it costs to do, we can get close to that, if not replicating exactly that level of detail by using the gravity and magnetic data and largely letting computers do the job. And so If you don't have any other kind of data, gravity and magnetics is a good place to start. Even if you do have a lot of data, it's still a good place to start, because if you can have that kind of framework from a regionally extensive and consistent data set, then you're probably a lot farther down the line when you go to do the high effort mapping that comes from the data richness that if you have that available. The only caveat I would add is that you really do have to have good geopotential fields data in order to do that kind of job. And this is a case of where you kind of get what you pay for. And looking at Texas, you can probably recognize the county outlines there for those of you who are from the region, but it doesn't really matter where it is. This is a pretty typical kind of situation around the world. There are publicly available potential fields data that come from stations that are relatively sparse in the public record, but can be very closely laid in data that's available from vendors. And the same thing for magnetic data. So provided that you have a good data background, that hard work of mapping regional basement involved faults can be done in a preliminary way quickly and over a large area if you use the right kind of data, and we can do it. So thank you very much for listening, and if I've got any time left over, I will send that over to the next guy so he can be a little more, take a little more time. Thanks.